All right, so we're going to start with some background stuff that you already know, and then we'll slowly ease into the couple of problems that we want to look at today. And you can see this now. By the way, are you seeing my
the slides?
Just the slides, or you're also seeing some other things?
Just the slides.
Just the slides. Okay, good. All right. So here's what we know, and this is stuff that we discussed. We said that if we are given n numbers, we can build a red-black tree to do the three basic operations: insert, search, and delete, and all three can happen in log n time. This is our basic red-black tree stuff that we discussed. You don't need to understand red-black trees, Ariana. All you need to know is that with a red-black tree, I can take n values that can be compared and put them into the tree, and I can do insert, delete, and search. If you don't know this much, then you're in trouble. But if you know this much, you can get very far even without understanding how red-black trees work. Is this clear, Ariana?
Yes.
Okay. All right. So that's why this case is called the dynamic case, because the set of items in your search tree is dynamically changing. Things are being added, things are being deleted, and occasionally you do a search. Okay. Now we actually figured out some more. We figured out that we can augment this tree with information such as the size of the subtree. And by doing so, we can now answer a couple more queries fairly efficiently. One is called the rank operation. The other is called the select operation. And both of these can run in log n time. Now, the rank operation is, if I give you an item, it'll tell you what is its rank in the sorted order in the entire set. And the select operation will help you to pick out an item with a specified rank. Now, remember that the reason these operations are interesting is because the case is dynamic, in the sense that the ranks are constantly changing. And so if you're selecting the kth item, it might change depending on what inserts and deletes happened prior to that selection, right? So this is what we know about red-black trees. Now, as I said, this is really the dynamic case, but we can also take it one step further and answer what are called as range queries, where I could say, tell me how many items are between values x and y. Now, it turns out I can solve this in log n time as well. Can either of you tell me why you can solve this in log n time?
For here, does the x and y represent the index?
No, x and y represent values.
Oh, okay.
If it's the index, then it's easy. Then it's y minus x. But if I give you items, remember their ranks actually can change. So you really don't know how many items are between 10 and 20. It all depends on what items got inserted and deleted at the time prior to the time where you ask this query. So why would this query be answerable in log n time?
If you know x and y, you can find the nodes that are between those two, and then you'll be able to then you can calculate that distance and then find how many items are between them.
Okay, Adriana, any thoughts on this?
Well, what if wait, no, never mind. Because if it's a red-black tree, it's sorted. So if it's already sorted, then you just have to find the numbers in between, right? So that's why, because the red and black tree sorts the item.
What did I say about red-black trees? What is up there?
It can do insert, deletion, and search.
Yeah, what does it say below that?
You can augment the red and black tree with the size of ranking an item, selecting an item.
Yeah, why is that relevant for range? So range of x comma y simply says how many items are between the values x and y. Now, if I find the rank of x, which I can because I know I can do a rank operation, and if I do the rank of y, what does that tell me about how many items are between x and y?
Difference.
Adriana, you see that?
Yeah, the difference, right?
Yeah, so it's the rank of y minus rank of x. Maybe you have to add a +1 to it. Is that clear? Well, you either add +1 or you subtract 1, depending on whether you want to include x and y or not. You may have to check whether x and y are in the set itself. It's possible x and y are not in the set. So there are some minor cases, but more or less, it's basically 2 rank calls. Okay, so it's as easy as that. Since each rank operation takes only log n time, I can do range operations in log n time. So I don't need to actually go through the tree and figure out how many items are between them, because that would be too much work. Because a range query could ask you what's the range between, let's say, the smallest item and the largest item, or the middle item and the largest item. And that may be too many values. So you don't want to spend order and time counting how many things are in between. Whereas if you do a rank, I can quickly figure out how many items are in between. Now, all of this is useful because I can manage things in a red-black tree. And this is a dynamic case in the sense that it works even if I am allowed to insert and delete frequently. Now, here is some more that we know. If I'm given n numbers, and let's say that I want to look at the static case, which means that there are no inserts and deletes. Okay. Now, instead of storing it in a red-black tree, I could store it in a sorted array, because I'm not going to have inserts and deletes. So the array is not going to get messed up. So I just have to sort it once and put it in there. Now I could do a search operation. Since I don't have inserts and deletes, I can definitely do search operation. And I can do rank and select all of these fairly efficiently. So this is the static case. Now, how much time does it take me to do a search? And why?
To search an item in a sorted array?
Yeah.
A big O of n?
In a sorted array?
Wouldn't it be log of n?
Sorry?
Oh, binary search. So,
I do binary search.
I'm an
That's
idiot.
right.
That's right.
Yeah. So I can do binary search, and so therefore it's log n. So the good thing is, if I don't have inserts and deletes, and if I'm only dealing with the static case, things are actually slightly better. But still, search takes you log n time, because I can do binary search. Now, how do I do rank and select? How do I find the rank of some item X?
Wouldn't it just be the same thing, but the index?
That's right. So you first do a search, and then you figure out what position is it sitting in, and that's my rank, right? If its index is 7, it's the 7th largest item. So the rank is obvious. And if I want to do select, that actually can be done in constant time, because if I want the 17th item, I just go to the 17th location in the array, right? So whatever I have on the slide is actually a little bit off. I can do select even faster than log n. I can do it in constant time. Are you okay with this? Adriana, everything okay with this?
Mm.
Are you sure? You don't sound too sure. Ask me.
Okay. Yeah, I'm fine.
Okay. So how do I do a search again?
You a search.
Sorry?
By finding the rank of an item. No, wait, never mind.
How do I do a search in a sorted array?
When doing a binary search,
Very
and
good.
it says a lot
Okay.
of runtime.
Yeah, search is done using binary search. Rank simply does a search and then simply reports the index in the array. And select simply goes and grabs the item from the location, and that's your select. Okay. Now, I can also do a range query. If I ask you how many items are between X and Y, how do I do this?
You should just find the rank of X and Y and then just subtract both X and Y to get the range.
So I just do a rank just like before for X, then do a rank for Y, and that gives me the two indices, and then I can figure out how many things are in between, right? Just do a subtraction again. So these are all pretty obvious, but it highlights a slight difference between the static case and the dynamic case. And it's good to know about this, because if your problem seems like a static case, you don't have to go to the trouble of doing the fancy stuff of red black trees. But if it is dynamic, then you have to go and do that work. Okay, but pretty much we see that we can do the more or less the same set of operations and more or less in the same amount of time, except that select in the static case turns out to be slightly faster. All right with that? Okay. All right. So now this is just to remind you of the things that we've talked about in the past. Now let's talk about one of the problems. This problem is the problem called triangular collection. Oh, I forgot to put the problem statement here, looks like. I'm sorry. Well, I know, Lazaro, you know this problem because you've tried it. Adriana, do you know this problem?
Mm-mm.
All right. Yeah, so Lazaro, do you want to summarize the problem for Adriana? Oh, here you go. Good. That's the problem. So you're given a set of positive integers, and you're told that these positive integers, think of them as the sides of a triangle, and you're asked how many. Well, you're told first that a set is triangular if any triple of these numbers can form a triangle, and you want to know how many such sets are there. It's a little bit hard to grasp so quickly, but I'm going to move on and try and explain how this is done, and hopefully it'll start to make sense to you. Okay. All right. So the basic idea is uses this triangle inequality that says that if there's a triangle with sides A, B, and C, and let's assume that C is the largest of these three, then the triangle inequality says A plus B must be at least as large as C. If C is not the largest, then this happens sort of automatically. You don't need to do much more. Okay, so if A and B are smaller than C, then A plus B must be greater than, actually it's greater than or equal to C. The reason it can be equal, by the way, if A plus B is equal to C, then one of them is in between the other two. In fact, B will be in between A and C. I'm sorry, A, B, and C are lengths. So then if A plus B is equal to C, then the triangle is really a flat triangle. It's all 3 points are collinear. Okay. All right. Now, here's a possible strategy to find all these subsets. What we can do is first we can find all possible triangles in the set, and then from there we can use that to find all possible sets that are triangular. Okay, or that forms a triangular collection. Now, for the first part, in order to find all possible triangles in the set, this is actually tricky because there are 50 to the power 3 possible triangles. You're told that n is equal to 50, and so the number of possible triangles will be with 3 sides is 50 to the power 3. Is that clear? Now, how big is 50 to the power 3? It's, even if you take it as 100 to the power 3, that's 10 to the power 6 roughly. Yeah, that's not terribly large. 10 to the power 6 is just a million. So theoretically, you could go and figure this out. But you might end up with some trouble, and I'll show you some tricks for how to do this faster. But let's just assume that you're able to do this. Then you've now figured out all sets of size 3 that are triangular. Your next job is to find, one way to approach this is to next find all sets of size 4, then all sets of size 5, 6, and so on and so forth. That's one possible strategy, but even there, we don't really know. It's not clear how to do that last step. So this is one approach, and it's sort of a naive approach. And there is a problem with this. And the problem is that if you were to do it this way, things will very quickly, they'll get out of hand for the last step, for the last bullet. And the reason is that the number of sets is actually very, very large. The naive solution can definitely find all the 50 triangles very quickly, but it becomes very inefficient because there are 2 to the power 50 such subsets if you have 50 different numbers. And so this becomes 2 to the power 50 is simply out of the question. That's, what is that? Well, 2 to the power 10 is 1,000, 2 to the power 20 is 1,000,000. Then you have a billion, trillion, so I guess it's somewhere near a quadrillion. Okay, and that's too much. We don't really have machines that can do so many calculations in roughly a second. So we have to come up with some other tricks in order to solve this problem. So here's a way around it. And I know, Lazaro, you've tried some things. So let me give you some ideas for how you might want to approach this. I'm going to define the following: n of AB to be the number of triangular sets where A and B are the smallest values in the set. Okay, so we really want to know if A and B are already 2 sides of the triangle, what can the third side be? What values can C take? This is what we want to know. Okay, now here it turns out that we can apply some tricks in order to figure out if we are able to do this somewhat quickly. If we can figure out for A and B how many triangles you can form with a third value picked from the set, then I could quickly try all possible pairs, and then the number of pairs is only 50 squared. Because A, there are 50 possibilities, B, there are 50 possibilities, and I want to do something quick for C, and so then it becomes 50 times 50 times something quick. Okay, so in order to achieve that, we're going to start with one observation that says, if A, B, C can form a triangle, so can A, B, D, where D is slightly smaller than C. Okay, so if you take smaller values, it's really not a problem. You may not be able to take larger and larger values of C, but if you want to take smaller values, it's not a problem. Now, this turns out to be something quite important, because now here's what I can do. If A and B are smaller than the third value, and if I want to know what is the third value that I can take that will form a triangle? Well, what I can do is find the largest C that'll work. And then everything below it will also work. And then it becomes a range query. Is this making some sense?
A little bit.
So I'll show you an example and hopefully it'll start to make sense. Well, actually, do I have an example? Maybe not. Let's see. We'll see. And in order to find the value C that's the largest, we know that it cannot be more than A plus B. Right? So what you do is you do binary search for A plus B, and then you find how many values are between B and C. And that gives you all the values that'll form triangles. Now, how quickly can I do that? Well, I can do that in log of n, because I can do binary search and range queries in log n time. And remember, this is a static set. Now, what do I mean by static set? I can take all my values A, B, the 50 lengths that I'm given, sort them, put them into an array, into a static array, and I can do binary search on this. So for every pair of values A and B, I find the third value C that can form the third side of the triangle, the largest possible value that can form a side of the third side of the triangle. And then everything in between B and C are values that'll work for me. Once I do this, it turns out counting becomes quite easy. Because now I'm going to take every possible pair, do this effort, and add all those values up. And I'm done. So these are only triangles so far. I still have to do a little more work, and I'll show you what to do there. Okay, so this will count how many triangles are possible. It doesn't quite count how many sets are possible. That's a little bit more work. Fine. So it may be a good idea to look at an example. And let me see if I can pull up the example. We might as well go to the problem set. Okay, here you go. So here was an example that was given to you. Are you able to see this, see the problem set? No? Okay.
Still shows the slide.
You're still seeing the slide. Okay, all right. Let me see how to get to that. Are you seeing it now?
Yeah.
Okay. All right. So if you recall, this is the problem that was given to you. Here's the entire problem. You're given a set of numbers, and in these numbers, you want to know how many sets are triangular sets or triangular subsets. A subset is triangular if every subset of it can form a triangle. Okay, that's what you're told. Now, here is an input. This tells you that there are 5 numbers that are given to you, and the numbers are, is that right? Yeah. And you're given 3, 1, 5, 9, and 10. And you're asked the question, how many triangular sets are present here? Now, well, the first thing we'll do is we'll sort this. And then we'll put it into an array. And so we would have 1, 3, 5, 9, and 10 in that order. Now we're going to ask if 1 and 3 are the two smallest items in the set, what else can you add to it? Well, first of all, which ones can form triangles? And in order to figure out what those triangles are, I just have to figure out which ones I could possibly add. Now, if it's 1 and 3, the third side cannot be more than 4, cannot be more than the sum of those two. So therefore, with 1 and 3, nothing can happen. Forget it, throw it away. Then I would try 1 and 5, and I would ask the question, what is the third thing I could add to it that'll form anything? And again, you'll see that I can't even add 9 there, because 1 plus 5 is 6, which is way smaller than the next larger item. Then I would try 1 and 9, and 1, 9, and 10 would work out. So that would give me one triangle. It's also one set. Then the next thing, I would start with 3, and I'll try 3 and 5 as my two smallest items in the set. And then I will ask the question, can I add either 9 or 10? And of course, the answer is no. So nothing will work out with 3, 5. Then I would try 5 and 9, and you'll see that 5, 9, and 10 would be okay as a triangle. And so it gives me two triangles right now, which is, what was it? I forgot already. 1, 9, and 10, 5, 9, and, oh, there should also be.
Professor, with the 1, 9, and 10, when you add up the 9 and 1, that gives you 10, but it should be strictly greater than,
Well,
right?
Sorry, if in the set, so you'll actually get quite a few triangles now. You'll get 1, 9, and 10. You will get. So what was your question again? I didn't quite hear you.
Yeah. So isn't the formula that it needs to be strictly greater than, it cannot be equal? So isn't 1, 9, and 10 invalid?
Well, actually, they never said this. They didn't say that you can't have a zero triangle. They didn't say that you can't have these. So I don't really know how they count it, but we'll know in a moment as soon as we finish our calculations. So clearly, one set would be 1, 9, and 10. The other set would be 3, 9, and 10. And the last set would be 5, 9, and 10. So there would be 3 triangles that are possible. And maybe that's what they've dropped 1, 9, and 10 and reported 2, because these two sets they cannot be merged together.
Also, in the clarifications for this, the competition, someone asked for this problem, do degenerate triangles count as a triangle sets? And they replied no. Okay,
so that answers your question. So you cannot have equal to, it has to be strictly greater than. A degenerate triangle is when one of the angles is a 0 in the triangle, right? So great. So I'm glad somebody asked, and I'm glad that it got clarified. It simply means that 1, 9, and 10 is not allowed. And so really there are only 2 triangles that are allowed, 3, 9, and 10, and 5, 9, and 10. Now, this only counts triangles. What we are interested in is our larger sets. So what we're going to do is we're going to add some extra numbers to your set just to see how this will work out. So I would say go ahead and add to 1, 3, 5, 9, and 10. Let's say we add 12 and 15. Okay. Now it starts to become interesting. So now we're going to ask the question. Well, let's just add one thing there. Let's just add 12 to that list. Okay. So after, yeah. So now what can we do? clearly with 1, you cannot have 3 as your next smallest item. You cannot have 1 and 5. You cannot have 1 and 9. And you cannot have 1 and 10 as well. So pretty much with 1 as the smallest item, you can't have any of the other guys. So next we move on to 3. With 3 again, 3 and 5 doesn't work out. 3 and 9, 3, 9, and 10 would work out, but not 3, 9, and 12. Right. So I guess you need to have a clear algorithm here. So here's what we do. If let's say we pick 2 of these values, let's say we pick 3 and 5. What we're going to do is we're going to do a binary search for 3 plus 5, which is 8. And we're going to find how many items are between the 2 numbers 5 and 8. And between 5 and 8, there's nothing. So with 3 and 5, you're not going to get any sets whatsoever. Then you will go to 3 and 9, and this time you'll see that 3 plus 9 is 12. You do a search for it. You leave out the 12, but now there is only 1 item in between, and that's 10. So that'll give you only 1 triangle with 3 and 9. Okay, so with 3, we've so far gotten 3, 9, and 10, and we're going to get 1 more that'll go 3, 10, and 12. Now, let's look at what will happen with 5. With 5 and 9, we're going to look for 14, which will now include both 10 and 12. And so the number of subsets that you can get with 5 and 9 as your starting pair is going to be all the subsets you can form with the other guys. And in this case, there's 10 and 12. So with 2 items, the number of possible subsets you can get is essentially 2 to the 2 minus 1. So that's 3 possible subsets. You can just have 10, you can just have 12, or you can have both 10 and 12. And so you count all of those. So with 3 and 9, you get 3 different subsets. And then with 5 and 9, again, you'll get three more subsets. With 9 and 10, you will get 1 subset. You add all these numbers up, that's your answer. Did that make sense? For whatever pair you take, let's say we take the first pair, we figure out where the sum lies. We figure out how many items are in between the second largest and the sum, and take all those, figure out how many different subsets you can form. Those are all subsets that you can add to the first 2 items, and they will give you subsets for the answer. And you keep adding these up, and that's your final answer. So in this case, the right answer would be with 1, 3, you didn't get anything. With 1, you didn't get anything. With 3, you got something with 3, 9. In fact, you got 3 sets with 3, 9. And then with 5, 9, again, you got 3 sets. And then with 9, 10, you got 1 set. So the right answer is going to be 3 plus 3 plus 1, which is 7. Did I lose you guys somewhere?
Yes. So for 3, 9, we add them up, and we know that C needs between 9 and that added up number.
Oh, sorry. So for 3, 9, you get only 1.
Mm-hmm. Okay.
Right? For 5, 9, you get 3.
How do you get 3?
Because you can take either only 10, only 12, or both 10 and 12.
Oh, you can take both. Okay.
Right? So 1 for 3, 9, 1 for 3, 10. I forgot 3, 10. Right? And 3 for 5, 9. And 1 for 9, 10. So what did we get? We got 1 plus 1 plus 1 plus 3. So I think we got 6, not 7. Sorry.
Okay.
Yeah?
Yeah, thank you.
So essentially, each of those things you got by doing just some binary searches. That's all you did. So with a sequence of binary searches, I can answer this for just one pair. And remember, the pair that you pick must be the two smallest items in the set. And if you add these for all possible things, then you know you've covered all your subsets, because every subset must have two smallest items, and you counted all those. And you're never going to count anything twice, because you fixed the two smallest items. Is it still a bit confusing?
So we know we always have to get 2, and those are fixed. So that is already be n squared, right?
Well, yes. So we have n squared pairs to deal with, correct?
Okay, and then the rest is just
Just log n.
Yeah, log n.
Yeah, that's
to
it.
that range. Okay.
So it's n squared log n is the time complexity of this algorithm. And since n is 50, 50 times 50 is 2,500, and log of 50 is about, let's say 6. So essentially, it's like 10 to the 2,500 times 6. So it's even it's about 100,000 or so, something smaller than that. And you have to do one sorting and store it in an array, and you're done. Okay, so that's what your algorithm is going to be. You're going to start with the set, sort it, put it into an array. Then you are going to write two for loops that will decide which are the two smallest items. For each of those, you're going to do a binary search for their sum and find the difference in the index between the second largest and the sum. And that will give you, and 2 to the power that number minus 1 will give you how many subsets you can form from those guys. So let's say you picked a pair, and let's say you figured out that between this pair and the sum that you have, let's say 7 items, just for the sake of argument. If there are 7 items, then the number of subsets you can form there is 2 to the power 7 minus 1. Remember, you have to take at least one, so the empty set cannot be counted. So it won't be 2 to the 7, it's 2 to the 7 minus 1. Okay. So those are the numbers you're going to keep adding for each pair. And then you keep a count of all that sum, and that's what you report at the end.
So we can just do that math and add it to an integer. We don't even have to store the valid subsets.
Yeah. You don't have to store any of that nonsense. Okay. Yeah. All you need is a count. Is this cool? Yeah, it's a nice problem. It didn't use anything fancy here. There are no red-black trees. Adriana doesn't have to worry at all. It's just sorting and searching and setting up the right for loops. But in order to do that, you had to understand quite a bit, right? You had to go through all that understanding. And this is why I explained to you why in the static case, I can do search, and I can do rank, and I can do range. These are all important pieces to understand in order to get this done. Okay. All right, can we move on? Adriana, questions? Did we lose you completely?
I think I got it. Like, we need two. We need to define two small. Two a
Two
pair of
smallest items, yeah.
items and figure out how many triangles
Subsets you can form with that. Yeah,
you can form with that.
yeah.
Yeah.
Very good. Yeah. Right. Well, as you ask the question, I'm just realizing that there may be one minor problem. No, we're all good. Whatever I said is good. That's fine. Any other questions? So one of the important things that I did not say, but it's true, is that if with the two smallest items, you can take any of those other guys and form a third side of the triangle, then no other triangle is going to be stopped. Everything else is going to be okay because they're only larger than the first two smallest items. So if you replace something with a larger item, you're okay because you've already tried the two smallest and the very largest, right? So you can replace anything in between and you're going to still form triangles and everything is going to be okay. And that's something we wrote down even on our slides here, because we said somewhere we said that if it works for A, B, and C, it also works for A, B, and D, where D is slightly larger than C, slightly smaller than C. All right, so this is roughly what I said already, that the amount of time is going to be 50 times 50 times log of 50. So that's n times log n. And n squared seems to be unavoidable over here. I do not know how to eliminate that. But this is already better than 50 times 50 times 50, and then going to find all subsets of size 2 to the 50. This is way better than that. Okay.
Like, could we use the counting principle to like solve this problem?
Can you speak louder? Adriana, didn't hear you.
The counting principle. I mean, I only know of it, well, heard of it rather, but like I don't know if we could use that to solve the problem.
So I'm not really sure what that means.
It's
But
something in discrete math. I don't know. It's called the counting principle. Like you count.
right. So again, if I understand this correctly, what we are saying here is that we're counting. Remember, we're counting different subsets. Now, every such subset has two items that are smallest in that subset, right? Depending on what those two items are the smallest, it'll fall into different collection that we are already counting. And so therefore, our count is going to be correct. Okay, so that's how we are using the counting principle, and that's how we convince ourselves that this makes sense and this was going to work. Should I repeat that?
No, it's okay.
Okay. All right. So much for the counting principle. Sorry, the triangular collection. We're now going to talk about some knapsack problems. I won't be able to get through the whole problem because it's quite a bit more difficult than the triangular problem. But let me help you to set the stage up for some of the things that you may want to do. Okay. So let me go back and explain basic knapsack problems, and then we can start to think about what is a bad knapsack problem, which is what the problem that we want to look at from the competition. So what's a knapsack problem? Here is what it is. It says, if I gave you a set of numbers, we want to know whether there's some subset of these numbers that adds up to a number B. That's called a knapsack problem. Another way that it's typically posed is that you're given a bunch of n numbers. You're given A1, A2, A3 up to AN. And think of each of these as the weight of an item that you want to put into a knapsack. But you're also told that the knapsack cannot hold a weight of more than B. It has a weight limit. And so you want to know whether I can pack this backpack, this knapsack with no, right up to the limit. Okay, that's our question. Now, if n is a large number, if there's more than, let's say, 50 items, then we really cannot test all possible subsets of S to see if they add up to B. Because if it adds up to less than B, we are not so happy. If it adds up to more than B, our knapsack is going to fall apart. So it has to add up to exactly B in order for us to go home happy. And if we want to do this, we have to, it looks like we have to test every possible subset, just like in the previous case. So somehow we want to avoid testing all these subsets. And the reason we want to avoid this is because there are 2 to the n possible subsets. If n is equal to 50, 2 to the 50 is just, as we saw, it's something like a quadrillion, and we can't deal with that. Okay, so what do? We use something called dynamic programming, and I'm going to show you with an example how knapsack is done using dynamic programming. Even though you may not know what dynamic programming is, that's okay. You're going to you should be able to understand what I'm going to tell you now. And then this is how to solve a good knapsack problem. And then maybe you can go home and start to think about what to do with a bad knapsack problem, or really a nasty knapsack problem. Okay, so here's how dynamic programming works. This is the basic knapsack problem. You're given 5 items that you can put into the knapsack. The first one has weight 1, the second one has weight 2, the third one has weight 7, the fourth one has weight 6, and the fifth one has weight 5. And you're told that your knapsack has a total weight limit of 11. Ignore the box at the bottom. We're asked the question, can we fill to capacity a knapsack with weight limit W equal to 11? Now, how do we figure this out? Well, you look at the weights there and you say, what numbers will add up to 11? You try all these various combinations, and ultimately, hopefully, you'll figure it out. Or you might figure out that no matter what combination you take, you're never going to make it to 11. That's also possible. So the way we do this is to build a big matrix. The matrix is going to have 12 columns, and they will be numbered 0, 1, 2, 3, all the way up to 11. And the reason it goes up to 11 is because the weight limit of the knapsack is 11. And the rows are going to correspond to what I've shown you here. The first row is going to correspond to the empty set. The second row is going to correspond to just the item 1. The third row is going to correspond to the set of items 1 and 2. Then the next row is going to have 1, 2, and 3. Then the set 1, 2, 3, and 4. And finally, the set 1, 2, 3, 4, 5. Those are the labels that I'm going to give to the rows. And the columns, as I said, are going to be labeled all the way from 0 to whatever the weight limit is. Now, I'm going to put in this matrix either zeros or ones. If I put a 1, let's say I have a 1 here. If I have a 1 here, it says that with items 1, 2, and 3, I can make up a knapsack of weight limit 5. That's what a 1 here would mean. If I have a weight limit, if I have a 1 over here, it would mean that with weight limit 8, I can do this as long as I have all possible 5 items to choose from. So what you see here is that as the rows go down, the choices that you have increase. Every time you have one more item to choose from. So therefore, once I have this table filled up completely, all I have to do is to look up this 11 and see whether I can achieve 11 using any of the 5 items or some combination of the 5 items over here. So if this box gets a 1, then I'm done. Then I know the answer is yes. If this box is still 0, then I know that you can never fill this up with, you can never fill the knapsack to capacity. Now, I'm going to show you a trick to fill up this entire matrix. And eventually you'll know the answer for whatever it is that you want. And in order to fill this matrix, there's a very, very simple rule. By the way, this corresponds to W. So here's how this goes. Since I've already filled up the first row, before that, let's take a look here. The first row is all zeros, and the first column is all ones. Now, what does that mean? All it's telling you is, if I have nothing, if I have an empty set, if I have no items that I can put into the knapsack, well, the only weight limit I can achieve is weight limit 0. Anything else I cannot. Okay, so all of these are zeros on the first row except for that first item. I have ones along the first column also, because I don't care what items I have. If my weight limit is 0, I know how to fill this up perfectly, and I know the answer is yes. All I have to do is to put nothing into my knapsack, right? So this is all 1, which says that I can achieve this weight limit of 0. This is all 0, which means that I cannot achieve weight limit 1 or 2 or 3 as long as I don't have any items to choose from. Right? Okay, now I'm going to give you a formula for filling up the next row, and then I'm going to give you a formula for the next row, and so on and so forth. Now, here's how this works. So we're going to assume, as I said, this matrix, I'm going to call this the matrix M. This matrix, M of j comma k, so the jth row and kth column, simply is a 1 or a 0 that answers the following question. It's a true-false question that says, can you fill a knapsack to capacity as long as its weight limit is k, which is the column, and as long as the items you can choose from is only 1, 2, 3 up to j. You don't have the entire set to choose from. You only have the first j items to choose from. So I will restrict myself to a smaller set to start with, and then slowly I'll relax the constraints until the end when I'll have any item to choose from. Okay, and here's the formula. The formula is very, very simple. It says that you can put a 1 in the jth column entry as long as one of these 2 conditions are true. The first condition says if m of j comma k minus 1 is 1. Now, what does that mean? Well, it means that if I can, I wrote something wrong there. I'm sorry. That should have been j minus 1k, not jk minus 1. I apologize. So it says that if I can achieve the weight limit of k with the first j minus 1 items, then I can easily do it with j also. I'll simply not choose the jth item. Right? So I should have said here j minus 1 k. Is that clear? I can fix this, but we'll just lose some time here. Or if the I'm sorry, I just have to fix this because I made 2 mistakes here. That's terrible. All right, let's fix this. This should say j minus 1, and it should say k. And this should also say j. Well, this could actually remain as j. That's fine. All right, good. All right, so here's what it says. It says that if in order to, let's see, in order to make this a 1, either the same row previous, same column previous row should be a 1, or I want, or I can now choose the first item, but there should be some other item, or I should be able to make j comma k minus weight of k to be equal to 1, which means without adding the kth item, I'm able to achieve 1 in the subset. So this is a mistake. This should be j minus 1, not j. I apologize. Should have been more careful. Yeah, that should be j minus 1. Okay. So either the item in the previous row of the same column should be a 1, or the item in the previous row but several columns away should be a 1. So in this case, what I can do is I can add the kth item, whose weight I know to be weight of k, and I know that I would achieve the total weight of k. So this is what I have here. Oh, this should be, again, stupid mistake again. Terrible. This should be weight of j, not weight of k. Yeah. How am I doing on time? Okay, I still have 6 minutes. Good. All right. So remember, I'm looking at the jth row, and I'm looking at the kth column. If this has to be a 1, then either the previous row same item has to be a 1, or there should be a 1 on the previous row, but a few columns away, so that I can add the jth item and I would achieve this weight limit. Remember, in going from the previous row to this row, I now have a new item that I could choose from. If I were to add that item, then I would have occupied some amount of weight of the knapsack already. So all I have to do is to make sure that I can pick the rest of the weight limit using previous items. And that's what we are doing. We're looking at the previous row j minus 1, and we only want to achieve now a weight limit of k minus the weight of the last item you just added. So this is what will happen if the jth item is not added. This is what will happen if the jth item is added. There are only 2 possibilities. And so both those cases are taken care of. Now, if you use that rule, it turns out you can easily fill this up, and you can continue this. It turns out I've made the same mistake in all the next slides, but you can start to fill this up, and you'll see here that soon it'll fill up the rest of the matrix, and you will get, you will be able to see that it fills up the entire matrix. Okay, now we can go over one of these examples just to make sure that you understand. So let's say we take a look at this guy here. Okay, in order for this one, this is a 1 if the previous row same column is a 1. In this case, it's not. So we have to look at something else. Where's my cursor? Yeah. So this is a 1 if the previous row is a 1, or in this case, we're looking at the third item, and we know that the third item has a weight of 7. So this is going to be a 1 if, in order to achieve 8, I can achieve a weight of 1 with all the previous items, which I know I can. Okay, and that's over here. This one says 1, so therefore I can achieve 8. So that's really what we are doing. Another way to think about this is I only have item 1, so I can only achieve weight of 1. If I use 1 and 2, then I can either achieve weight 1, weight 2, or weight 1 plus 2. Over here, we can achieve, definitely we can achieve weight 1, 2, or 1 plus 2. But because the third item is a weight 7, I can also achieve weight 7, or weight 7 plus 1, or 7 plus 2, or 7 plus 3. Okay, so those are the things that I can achieve. If I can add one more item, this guy is a weight 6, what will happen is I can still go with 0, 1, 2, 3, and then now I can also achieve 6, and I can achieve 6 plus 1, 6 plus 2, 6 plus 3, and then I can also achieve 7 plus 3 from before. Remember, this guy is the last thing is a 1 here because the previous row was a 1. So each one there tells you a story that tells you that, hey, you can achieve this weight limit, and it'll tell you exactly how to do it. It won't be written here, but it tells you that it can be done. So you apply this rule over and over again, and ultimately you will have figured out all the items. In this case, it turns out you can make up 11. By the way, how do I get 11 from these items? Can I do 11?
With
Yes,
4 and 5.
Yeah.
With 4 and 5, items 4 and 5, so their weights are 5 and 6, they add up to 11. Absolutely. Yeah. So that's your knapsack problem. Okay. Now this problem can be cast in many different ways. Sometimes they can be cast as change problems. Let's say you have coins of size 1, 5, 10, and 25. What can you do with this? How many different numbers can you achieve with that? So things of that sort, they're all knapsack problems. If your first coin has value 1, if your second coin has value 5, if your third coin has value 10, your fourth coin also has value 10, and your fifth coin has value 25, then you can figure out what all values, what all different totals you can make from these values. Okay, so those are all different kinds of knapsack problems. Now, all of this is dynamic programming. What we just did is dynamic programming. I'll explain all this to you some other day. Every dynamic programming problem has all these nice properties, and you can solve them in a very clean way, in a very algorithmic way. But let me just quickly introduce to you the bad packing problem. The bad packing problem says, I have a knapsack, and there are a bunch of items, and they all have different weights. Now, we do know how to fill it to capacity and whether it can be filled up to capacity. But what if I don't want to fill it to capacity? In fact, I want to fill it to as low a capacity as possible in such a way that any item I add will make it go over the limit. That's what the bad knapsack problem is. And it turns out that we can modify what we did for the good knapsack problem and solve this. I'm not really going to I don't have the time to do this now because it's quite a bit more complicated, but it's clearly very similar to the knapsack problem. We're not just interested in 0-1 answers. We also want to know how close we can get to the limit. And in this case, it turns out, by the way, in the previous good knapsack problem, it didn't really matter if we sorted the items or not. We could have, in fact, over here, we went with 1, 2, 7, 6, 5. We could have done this with 1, 2, 5, 6, 7 as the weight order. But when we do the bad knapsack problem, we have to sort it. And then it turns out to be somewhat more tractable. And I will explain this to you the next time. So we do have to sort this. And then there is a way to work this out. And we'll talk about this next time. but I encourage you to go home and try. There are some tricky parts to it. I still haven't figured out a simple way to explain to people, but I'm going to try next time. That's all I have for now.
Thank you, Professor.
Welcome.
Bye, Professor.
All right, you guys take care. Yeah.